please look at the code mentioned above and please sign up on Google Classroom. We have already started making some announcements. You will likely end up missing the announcements and you'll have no one else to blame to. The second quick logistical announcement is that we'll have an extra lecture on Saturday, 11th Jan at 11 a.m. in 101, so a lot of ones over there. And I think one or two people still have conflict, but in the larger pool we'll have like almost everyone available, so we'll have to stick to this time. FAQ and the projects which were earlier shared on Google Docs, I'll give all of you comment access on it, so that if you have any questions, queries, things like what is the max group size, what is the min group size, you can ask those questions if they're already not there. Also about projects, if you have any questions, like what is the expectation, if it's something is not mentioned clearly, you can please comment on the Google Doc and we'll get back to you soon. Also the video and the slides from the first lecture, the introductory lecture, have been put up on the course website, which is as mentioned in the slide above. This course website has also been now put on Google Classroom, so you can also get to that. Before we go forward, we should quickly revise what we started last time. Can someone tell me what is machine learning based on what we learned last time? We had looked at a couple of definitions. One was from Arthur Samuel, who, by the way, was the first person to coin the term machine learning, and he did that in 1959. So a long time back. Anyone? What is machine learning? Okay, the ability to learn without explicitly being programmed, that is correct. Any other definition you want to give? There was a more technical definition also, but we'll get to that later. Let's first start off with again the same definition as before. It's a field of study that gives computers the ability to learn without being explicitly programmed. Now, can anyone tell me what does being explicitly programmed mean here? Does it mean that machine learning involves no programming? So all the programming assignments are just a waste of time? Program itself. So is it some oracle which ends up writing the code? So who writes the program? Of course, there is one caveat, because there is something known as neural architecture search. We're not going into that. But who writes the machine learning programs? So do you explicitly program? What is the exact meaning of without being explicitly programmed? You don't hardcode cases. Okay. Can you explain what does mean?
You don't call in saying that this case is satisfied.
Okay.
There is more freedom.
Okay, good. So he's on the right track. Let's take an example to get this concept even better. Can you see these small digits over there? These are digits from 0 to 9, and these are from a dataset called MNIST, one of the most popular machine learning datasets. Now, the first task for all of us is we want to now write a program to recognize the digits, and we'll start with 4. Can someone tell me how they'll recognize if a digit is 4 or not? We're looking at these specific rows. What are some of the attributes of 4 that you see? Okay, can we start off as 4 can be thought of as a vertical line, a horizontal line, a vertical line, all of them are joined, and then another vertical line going down from the last vertical line. Can we think of that? Is that all that is there to 4, or is there anything more? What about the fact that the height of each of the vertical lines need to be fairly similar? Can we write this kind of a rule? Or do you see 4s where one of the line is very, very long compared to the others? Generally not. So you have to import some of these constraints. But are you done, or is there anything more? Just look through the examples of fold. Do you see any fold which would violate the rules that we specified thus far? And it's hard to look at. Okay, the second last is one case. What about this one? Okay, so each of the vertical lines, could it be a little slanted? In many cases it would be, and if I were to write, you will not understand which of the letters I've written. So, because people write differently, so that's another rule that you write. Now, what do you mean by slight slant? Does it mean that it can have an inclination of some 10 degrees, 20 degrees, 30 degrees? Where to decide that number from? So let's say you come up with some number based on your experience, based on some rules of thumb. But is that all? No. Some people write 4 with a slant, right? If you look at this 1, 2, 3, 4, the fifth 4, you have this particular line. You have a joint like this with a 45 degree angle, right? So that is now another rule that you've written. You have already come up with 5, 6 of such rules, but that's not all. Anything else you can think of? Thus far, we have not talked about the width of the lines. What can you think about that? Can we come up with some rules? Let's say if I'm writing with a different marker, or if I'm using the pen in a different fashion, will some of my strokes be wider, will be thicker, right? So maybe that's another particular rule. That there can be some cases where the width of each of the stroke is a little different. You'll have to again capture some of these characteristics while writing some rules or writing a program to recognize 4. So what we have done thus far is explicitly programmed to classify or to recognize 4, right? So now do you understand what is explicit programming? What we do is completely different from this. So what we've thus far done is we had data. Data was these examples that we already had. We came up with some rules. So these were rules which we as experts suggested. And in traditional programming, we have some kind of a Python or some programming language we'll write, which will recognize all of these. Of course, what is presented as a vertical line, as a horizontal line, are still higher constructs. For example, a vertical line, a computer does not know what is a vertical line. So you'll have to again boil it down to the computer. What do you think the vertical line to a computer means? Same? Same x-axis. So think of it as pixels, and all of the pixels will be of a similar shape, right? Vertically going downwards. So we have data, rules, and traditional programming that gives us the answers. Now let's go back to the definition. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Can you now tweak this particular flowchart to tell me what, if you have to replace traditional programming with machine learning, what do we need to do? So we're not explicitly programming. What changes? Rules are gone where? Yeah. So what we're saying is ability to learn without being explicitly programmed. So we do need the data, we do need the answers, and what we end up with is automatically some notion of rules that is being learned, right? So this is how traditional programming is. The paradigm of traditional programming is very different from machine learning. Of course, I've still done this in a very abstract sense. We'll slowly go into more details of this. We also looked at another definition, which is a more formal definition of machine learning, which was given by Tom Mitchell. Tom Mitchell. A program is learning from experience E. So look at the keywords: experience E, tasks T, and a performance measure P. If the performance is improving in the particular task as measured by the performance measure, and it is improving with experience, right? So let's say in this particular case, the task is what for machine learning? to classify digits. And what is the input that is typically given? You will have some, so you said that you have some experience. The experience can be you have some images along with the true label. So you have an image like this 0, along with that a label that it's actually 0. Right? We'll have many such examples. And the performance measure P. What do you think is the performance measure P? What do you want to optimize on? How correctly you are able to classify digits, right? So could you come up with a more scientific succinct term for correctness? Accuracy. Or similar such terms. We'll look at some of these metrics in today's lecture. So we'll start off today's lecture after having revised what is machine learning. We're now starting a company. All of us are starting a company. And we want to beat Big Basket or Grofers or some similar grocery store. We want to scale. So if you remember, one of the key words which we use a lot in the previous lecture was scaling. The problem statement is that we want to predict the quality or condition of a tomato given its visual features. So we say that our business use case is that Grofers or similar such grocery stores, they have some human in the loop who looks at each of the tomatoes, and that takes them, let's say, 1 minute per tomato, right? So there's a lot of human effort involved, which is making the whole process slow. We plan to scale it by using computer vision, visual features, machine learning, etc. What we'll say is we have now an assembly line. You put the tomatoes in the assembly line, and as they pass through, snapshots are taken, and you automatically classify whether it's a good tomato or bad tomato, and bad tomatoes are thrown away, right? So you're saying that you're saving a huge amount of human effort involved, and you're making the whole process quicker. So you're saying that via this process, you're able to make deliveries quicker, right? So let's now think what is the machine learning aspect in this problem statement. So if you remember, we have thus far just spoken that there is an inherent need of data, right? There is an inherent need of experience and data. So let's say that we have some past data on the quality of tomatoes. You have collected thousands of tomatoes, and for each of the tomatoes, some human expert quantified whether it's a good tomato or a bad tomato. For now, let's just limit it good or bad and not on the scale of how good or bad it is, right? Just two classes. So what visual features do you think would be useful to characterize a tomato? Color. So what do you think would be a good tomato? Which is more red or more something on the shades of red. What is a bad tomato? Something which is either showing some greenish shade. It may be unripe. Black definitely, or if it has some fungus or some other attributes. What are the other attributes which make a tomato good or bad? The shape. It is a
whether it has shriveled or not.
shape.
It is a perfect circular.
Circle or not? Okay. So the size is another attribute. Let's say that we assume for now that all tomatoes are roughly oval, and smaller tomatoes are bad. Very big tomatoes are also bad because they have been injected with some growth chemicals. Size, color we have seen. What are the other things you typically do? Sorry? Yeah, but visual features will not look at the field. So you'll have to get some proxy for that. So that is another thing which I want all of us to take from a machine learning course. What are some of the proxy features we could think of? Yes, texture. So texture will tell us something about the feel of the tomato, whether it's very rough, very smooth, or very blighted, etc. So we look at these three specific features. Could there be others? Yes, there might be thousands of other features, but for the purposes of this example, let's stick to only these three. So we were talking about some past data or some past experience that we already have. Maybe it exists in a form of a table like this. You have some sample number, you have the color, size, texture, and you have the condition. So this condition has been manually annotated, written down by a human expert. So in this particular table, do you think the sample number could be a useful attribute or feature to predict the condition? How many think yes? How many think no? Okay. Now tell you that it could be a useful feature. Now think more into it. How could the sample number be a useful feature? Sorry. No. So the question is orange. If the color is orange, the size is small, the texture is smooth, I can roughly say if the condition is good. But does sample number equal to 1 tell me that the tomato will be good or bad?
Yes. 1 and 2 are good. 3 and 2 are bad. We sequentially arrange all the good tomatoes first and
Okay.
then like without stratifying the data.
Okay. But why do you think the sample number could be useful? So some of you are getting to the point that let's say if you sequentially arrange, then we'll get something. But are we getting to some point? Yes.
Along with time, the features might change that can qualify good tomato and tomato.
Okay. So he's answering that maybe there is a notion of time associated with samples. Very likely there could be. And imagine a scenario where there is one specific time of the year, maybe when all of the tomatoes are bad. Maybe the producer was bad, maybe the vehicle which was bringing the tomatoes had gone rogue, something would have happened. So in some very limited cases, the sample number could be a useful feature, but it's more likely that it's probably better to include more features which are capturing the kinds of things we're looking at. For example, what was the vehicle condition or how many hours have passed since the tomato was picked up. Things like that. The sample number might be picking this up, but then this could be the same example as we saw in the last lecture, where more ice creams means more sharp attacks. There was some correlation, but there was no correlation. So we have thus discussed that the sample number is likely or unlikely to be a good feature depending on how we model the whole process. So for now, let's ignore the sample number. Imagine it does not provide us any useful information. So then we have some data table which looks like the following, right? We'll call this entire table the training set. And if you've noted, I've labeled them in different colors. Anyone wants to tell why these are in different colors? Okay, input and output is a very technical term. Any other term you could talk tell us about these two parts of a so-called matrix. So this looks like a matrix to you, 2D matrix. Experience and performance. So the condition is not really the performance. The condition is the annotation or the label or the output assigned to this particular. So this is one tomato, the next row is one tomato, etc. It's not really a performance. We call these things as features, attributes, or covariates. If you go back, let's look at the question which I was asking. What visual features do you think will be useful? Make sense? These things are called features. The first three columns in this table are called features. They are telling us something useful about the tomato. What is the fourth feature telling us? So it's also the first. By the way, features, attributes, and covariates are all used synonymously. But you can generally use features or attributes. Covariates is generally used in some other literature. And the output, or the condition in this case, is called the output or the response variable. What is the response once you've observed some features, right? Everyone clear till now? Now, we call this a training set. And let's, for now, introduce a bit of formalism. We'll call this entire matrix as D, right? We call this feature matrix. It contains n samples. What is n here? N equal to 4 samples. And what is the features in this? The number of features is color, size, and texture, which is 3 features, right? So the matrix X shown in the shade of pink is a 4 rows, 3 columns matrix. It contains n samples which are p n, right? we can write an individual sample as this, as something like this, like x1, we can write as orange small smooth, orange small smooth, right? Does anyone want to tell me why x1 is written in a column format where in this particular matrix x1 appears in a row? Why? So that is the operation. Yes. So typically when you consider the features or you consider a particular sample, you consider that to be a column vector, right? So this is where now we're starting to reduce a little bit of notations. Each sample is a column vector which is what dimensional now? What is the dimension of this? P dimensional. P equal to 3 in this case, orange small smooth 3, right? Thus can we write X as xi transpose where I varies from 1 to n, right? This is x1 transpose, this is x2 transpose, the third row is, can in fact do it. The third row is x3 transpose and x4 transpose, right? So we are able to now write the matrix X in terms of the individual elements. Similarly, we have an output vector Y. Now this is going to be one dimensional, right? Because for now, for this simple example, we have a single output variable or response variable, which is going to be Rn, right? Because we have n examples. Can we thus write this training set D as a set where we have xi transpose comma yi and I varies from 1 to n, right? So this way we are able to create this entire training set in a concise format depending on the ith sample, right? So again, xi is a p-dimensional vector and y is an n-dimensional vector. Everyone clear thus far? Now, the prediction task, this is where machine learning lends utility, right? If we only had trained set, there is no as such use for it. What we wanted to do was for unseen samples or for these samples for which a human has not yet annotated whether it's a good tomato or bad tomato, you want them to be passed in an assembly line and a computer vision approach, which there's some camera which is looking at these tomatoes. You want to tell what is the condition for them, right? Is the goal clear to everyone? So for future unseen tomatoes for which we don't have a human annotated answer, we want to tell whether the condition is good or bad, and then we want to accordingly process. So we have for these unseen samples, and I have drawn a line to separate these out. For these unseen samples, we still observe the input features. We still observe the color, size, and texture as given by the computer vision system, right? But we don't know the condition, and that is what we're trying to do. Yeah? We now break this whole matrix into two subsets. The first we've already discussed is the training set, which we said was the matrix D. And now we have the test set, where we have these specific entries on the condition as unknown, which we're trying to estimate predict. Right? So testing set will be fairly similar to the training set, but it does not contain the labels for the output variable. Right? Everyone clear with the distinction between training and testing set? Okay, so given the background that we have thus far, could you now tell what we are trying to do from this example in a more succinct fashion? What do we hope to do given the training set, given the test set? And we have to have some learning component. How do you relate the input to the output? I don't need a precise answer, but you can relate, you can write the output as some function of the input. Thus far, we don't know what kind of a function is this, and different algorithms will come up with different functions relating the output to the input. But we want to be able to predict the output using some functional form, let's say, for now. And where do we learn this f from? This function f from? from the training set. And where do we apply this function f on? On the testing set, so that given this, for this particular sample, given the inputs red, large and rough, you want to predict the condition, right? And the general hope would be that we're able to do this accurately, otherwise it does not make any sense, right? Okay, now a big question. Is predicting on the test set enough to say that the model is generalizing? Why or why not? The test set might be missing out the outliers. Okay. So Vino is saying that the test set might be missing out the outliers. So you can add a little more weight here. Okay. 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 So the answer that he is giving is that there could be some exceptions. There could be some outliers. But that is getting to the right answer. But you need to make it more general. The case that tests don't have annotation.
So what will we take?
What will be?
How will you check accuracy?
How will we check the accuracy? So we'll come to the specific question that how do we check the accuracy. Yeah, so we'll come to that. But yes.
The test set might be a subset of the train set. Then we can't.
Okay. The test set may be a subset of the train set, and your answer was that the test set might have some outliers. Both of you are nearly there. Consider some. Sorry.
Overfitting, right? So it's good. Work on
So we have not thus introduced any term like overfitting. Can we use some simpler term that we have seen thus far? Think of some terms you might have heard in some probability course. So the ideal thing that we want to do is to be predicting well on all possible inputs, right? So the emphasis is on all possible inputs. But can we test that? Can the test set be all possible inputs? Maybe in an ideal case, yes, but in a more practical case, no. You will never be able to enumerate all possible test cases. And now relating to the answer which some of you have already given. So one way to put it would be that the test set is only a sample from all possible inputs, right? So this now answers, or this now relates to the answer where you're talking about outliers. You could end up choosing a test set which is which contains a lot of outliers, but does not contain the outliers which might be present in all possible inputs, and also relates to your specific answer that the test set would be a part of the train set because it's now only a sample from all possible inputs. More generally, we have to let's think of it as there is some oracle or there is some generating process which generates the train data, which I am calling here as the empirical data sample. And I've written a technical term here, IID. So this is identically and independent distributed. If I would recommend that if you don't know this term again, you go back and study some of the prerequisites mentioned. You sample from the hidden truth or you generate data from the glue process. You're able to get some train data, which you learn, you get a model, which in our previous case was some function f that we were learning. Once you've learned that function, you predict using unseen data, you predict on another sample. So that sample is again also coming from the same data set, from the same underlying distribution or the same generating process, right? Hopefully. So what now we're getting is that the training set and the test set are samples drawn from the hidden true distribution. Sometimes this is also known as population. So you're getting some samples from the population, right? So the test set will not contain all the samples. In order to say that our model generalizes perfectly, we would have had to see the entire population, which is never the case, right? And we have a much more deeper discussion on the differences between the test set and the true population when once we study bias and variance, which are some topics which we should hopefully discuss in the next lecture. Everyone clear till now? Okay, so we have thus far seen one particular type of machine learning task where we were trying to classify whether the object or whether the particular tomato is good or bad. We now look at a very different example. We want to predict the energy consumption of IIT Gandhinagar campus, right? So again, the same exercise. What factors do you think the energy consumption should depend on? Weather, can you quantify that again? Because weather is again multi-dimensional. One specific aspect of weather. Humidity, temperature, okay. What do you expect the, so if humidity is more, do you think the energy will be more or less? More? Okay, what about temperature? If temperature is more, would energy be more? Why? More air conditioning cost. Okay, what are the other factors the campus energy to depend on? Health of the length. Okay, the number of people, number of occupants. And if there are more occupants, do you expect more energy consumption? Generally, yes. Any other factor? Sorry. Okay, functionality of the campus, or there are some other aspects of a campus energy, the internal management, which always requires some amount of energy. Okay, what other aspects? Sorry. Please.
Labs which use machinery.
Lab usage, or let's say, machinery, or let's say IT equipment. So if you think number of computers could be one example. So more the computers, more the servers, you generally expect more energy. Any other factor you could think of? Weekday, but that is in some sense captured by the number of occupants, right? So we don't have to explicitly write whether it's a weekend or a weekday.
So how, that is daytime time.
Sorry?
Weekend, how does that relate to the population?
Okay, so the question is how does weekend or weekday relate to the population? So I'm saying that in some sense, when it's a weekend, you would assume that many of the people are, let's say, not in the campus. So does the population automatically reduce? So we're saying that the weekend population would be lesser and the weekend energy would be lesser. Yes, what are you saying?
Weekend we are free. So basically we'll be playing and using more internet.
Okay. So you could always come up with some counter arguments. Yes. But there will be some people who would be leaving, some people who would be coming.
The day and night time.
Day and night. Okay.
Which are different day.
Okay. So he's saying that the hour of the day is also an important factor. How can you again tell us which hour you expect more energy consumption?
So in night people are sleeping. They can assume that night time people are sleeping.
Yes, you can assume, but we're not sure. But for now, let's assume that classes start at 9 and people have to sleep X number of hours. So in the night time, you generally see the load to be low. At least in the residential complexes, we expect that. So more people, generally more energy, higher temperature, generally higher energy. Again, can we construct a table like this now? We have people, temperature. I'm just for the purposes of illustration considering only two factors: people and temperature, and energy in kilowatt hours. It could have been some other unit also. We could use joules, but kilowatt hour is more generally accepted in certain literature. Now, what is the training set here? The first three rows, and we consider them as training set because they have the labels also mentioned, the output variable or response variable also mentioned. Whereas the set shown below of the last two samples becomes a test set where the labels or the response variable or the target variable or output variable has not been mentioned, and this is what you're trying to predict, right? So we have thus far seen two different kinds of examples. Let's try and make them a little more abstract to see the classes of two specific classes of problems. I'm going to write the first class of problems as classification. Here the output variable of concern is discrete in nature, right? Does everyone here understand what is discrete? So discrete means it could be one of few classes. It could either be, so this one of the example of discrete is binary, whether it's on or off. It could also be ternary, one of three classes. It could also be multiple number of classes. More formally, we say that yi belongs to a set from 1 to C, where we have C classes. We have seen one example. Can anyone tell me more examples of classification tasks you might be interested in? Sorry?
In a stage, in a cricket,
Sorry. In a cricket
in
team,
any sports, someone is winning.
who will win? Okay, so the example that is given is giving if you want to predict who will win, right? So in fact, this reminds me of some very interesting simulations. So I think there's a very nice blog by Nate Silver. Those of you who follow sports as well as data science should be really looking into that. And some of these blogs, in fact, predict the winners of the football Champions League and the NBA, etc., even before the matches start. And they have some confidence with which they say who is going to win the league, etc. Okay, so what are the kinds of results you have? Let's focus for now for something like cricket. Win, loss, or tie or draw. Let's say 4 particular cases. So this is now 4 classes. Yes. And what kind of input features do you think you'll have to get? And everyone else can also take a shot. So if you want to predict whether India and Sri Lanka are playing correctly T20, who will win? So how would you decide that? Well, playing 11. So playing 11 by by playing 11 do you mean the names? Probably not. So some notion of the ratings, right? Although having said that, only yesterday I read about a very interesting article. So there was some research paper which mentioned that someone was treating chess playing as a pure natural language processing game, and not looking at the inherent notion of what a move means. So they just gave it a specific EC4, etc. And that was also able to perform really well as a chess task. So those who are well versed with NLP might find this very interesting and shocking at the same time. Okay, for cricket, maybe we are looking at the player ratings, maybe the player age, maybe the fitness level, something on that sort. Sorry?
Source of last names.
Yes. Stadium, if there are home versus away. And in fact, if any of you played games like FIFA and Manager mode, you already know that they take into consideration many of these things and they're able to simulate whole seasons. Okay. Any other classification task you can think of? Indoor? Indoor, outdoor scene. Okay, so someone has taken an image. You want to classify whether it's an image or it's an indoor scene versus an outdoor scene. You have now 2 output classes. And what is the input that you're given? No, the input would be an image, right? Input now would be an image of some height and some width. So, but previously, if you look, the kinds of inputs that we had were fitting into matrix. So each sample was corresponding to only, let's say P features. But now you have a, let's say P cross Q matrix. So again, you have to figure out how do you encode the P cross Q matrix into that particular scheme which we have. Okay, any other example? Okay, will it rain tomorrow, will it be hot, or will it be windy, etc. Okay. Will I get a loan or not? Depending on some criteria, will I pass the machine learning course or not? Will I remain awake till the end of the lecture or not? What is the quality of food, good, bad? And you can have multiple such classes. What grade will I get in this class? A, B, C, D, E. Although for the specific question of grade, this becomes a very interesting topic. We'll talk about this later. There is also some notion of ordering associated with grades. You can sometimes quantify the relative order. We'll not go into detail about that one. The second example that we saw fits into something known as regression. The output variable was continuous in nature, right? To a large extent, we can assume that. So we can write yi is a real number. Okay, give me some examples of regression tasks. You want to predict a real number.
Amount of rainfall in
The
amount of rainfall.
the amount of rainfall. So that's genius. I think I've written that point. Stock market. What do you want to predict? The price of a particular stock. Okay. Any other example?
Runs scored by a particular team.
Sorry.
How many runs are scored?
Okay, how many runs will your team score? Again, so very interesting points you're raising, some of them, because again, if you look at some of the sports, people have already come up with some rules of the thumb. If you are only 3 batsmen down in cricket, after 30 overs, you double. Something like that. You can always verify those rules. And before we get into the actual algorithms, I wanted to talk about the performance measure P, which we discussed in the definition. So we had talked about experience E, task T, and performance measure P. I thought it's more important to first understand what different metrics mean and what does it mean that you have done a good job in machine learning or not. We'll start off with some metrics for classification. Let's assume that we had a ground truth Y. So ground truth means the correct labels that we've got. So let's say we had a particular set of tomatoes. For the first tomato, we know that it was good. Some human annotated it. Second tomato, someone said it is good, and the other three, someone said some expert labels it as bad, right? And then there is some algorithm, some function f that we've learned, right? That ends up predicting good, and bad, and we call this vector as y hat. So we'll use this hat a lot in machine learning. Hat generally signifies an estimate. What is your estimate of the status of the tomatoes, right? So it is y hat. And ground truth comes from the actual training set. For now, let's assume we have somehow, whichever set it comes from, we know the ground truth. And the prediction is made by the model, right? So what are the different metrics we could use to tell whether we have done good or not? What do you think? Have we done a good job in predicting? Or have we done a bad job in predicting? Bad job? Okay, how many things you have done good? Okay, why? Sorry? Depends on the? Okay. Okay, the answer is depends on the state of the art, which is a very valid answer because what he's trying to say is that you want to contextualize the accuracy or the metric that you've reported. Just saying I have 80% accurate does not mean anything. Only if the best reported thus far was at 60%, then 80% accuracy means a lot. We first look at a very simple metric called the accuracy, which basically tells us that how many you look at the accuracy across you look at the predictions across specific rows in this, and how many times is y hat equal to y divided by the length of y hat or y, right? So how many times have we accurately or correctly predicted the label? The accuracy in this case is, in terms of proportion, is 0.6, in terms of percentage is 60%, right? So it tells you one specific number, but this is often not enough. And there are different cases in which we need to again contextualize it. Let's look at some specific types of data to motivate some of the metrics. Let's imagine that we have 101 samples. Again, you're predicting something which is on a scale of which is either good or bad. And we have 100 samples where the ground truth or the actual samples are good, right? And one sample where the actual quality is bad, right? Now, there could be multiple cases in which such kinds of data sets exist. For example, in cancer screening, we would hope that in most cases, cancer screening will have people's health is good. They don't have cancer. Unfortunately, for very small, there will be cancer. But in general, if we look at some data, we'll expect it to look something like this. Good, no cancer, and cancer, right? So you end up with an imbalanced data set. And maybe even for planet detection. If someone is trying to detect from some imagery or from some feeds, most of the times you'll have no planet, and some planet, because otherwise, people would be getting Nobel Prizes every other day. Now let's look at a different metric now. It was called precision. Let's look at again the ground truth, the same table as we looked earlier. Now, before looking at this slide, can someone tell me what do you understand by the term precision? In general English terms or in layman terms? Sorry?
Repeatability of any task.
Repeatability, okay. What does it mean to be very precise? Deviateless, okay. Any other thoughts on what does it mean to be precise? What do you mean by when someone asks, can you speak more precisely? Or can you write down this more precisely? Sorry? To the mark. Okay. Could you think of precision in terms of whatever you're writing or whatever you're predicting or output that you're giving? How true that is? Or how much sense that does make? So in more English terms, in layman terms, it might mean that how much sense does it make what you're writing? Right? So now coming to a more formal definition, you look at the times you've predicted good, right? You predicted good how many times? 1, 2, 3, and 4. Out of these 4 times you predicted good, how many times were you actually good? Or was the ground truth also saying good? Right? So you predicted good 4 times, but you were not very precise in predicting good. Your precision was thus 2 over 4, which is 0.5. Right? Does everyone get the definition? How precise are you in predicting a particular class? Now, precision can be defined in terms of the specific classes. You could also define precision for bad. Right? What is the precision for bad? You predicted bad once, but for that specific time it was actually not bad. So you have got 0 precision in predicting bad. So precision for bad would then be 0 over 1 equal to 0. Precision for good is now 2 over 4. Right? Or more technically, you would write the fraction of relevant instances amongst the retrieved instances. Right? Now we come to another metric called the recall, which is of fairly similar notion. Now, what does the English word recall mean? What does it mean that person X has a very good recall? Able to remember, right? Something on that line. So the definition of recall is how many times it was actually good, how much of that you're able to recall in a prediction, right? So it was good here, here, and here. We've shown it through the arrows. We've been able to recall 2 of these 3. So 3 times the condition of tomato was good. We've been able to recall 2 times. Thus, the recall is 2 over 3, which is 67%. Right? Do you see the difference between precision and recall? Everyone with me till this one.
Example again. We are trying to predict whether a tissue is cancerous or not. In the ground truth, we see that we have 100 samples, out of which only one of them has cancer, which is the last sample, which is shown over here. And when we are predicting, we predict 99 times that the person or the specific sample is not cancerous, and 1 time, which is the first sample, we predict it to be cancerous. Right? So now let's try and understand the precision and recall for this set of predictions. The accuracy of the system is fairly good. Out of the total 100 times, we were accurate 98 times. The only 2 times we're getting wrong is 1, the time for the first sample when we're predicting it to be cancerous, while in ground truth it is not cancerous. And the other time we're getting it wrong is when we're predicting it to be not cancerous, and the ground truth says it is cancerous, which is the last sample. So the accuracy is 98 times you've correctly identified out of the 100 times. Now let's look at the recall. Out of the times the ground truth was true, which is the 100 sample, only a single sample, do we predict it to be cancerous in our prediction system? No. So out of one time where it was actually cancerous, we are not able to recall that prediction correctly. Thus, the recall is 0 or 1, which is 0. Let's look at the precision now. Out of the one time which we are predicting the tissue to be cancerous, was it actually cancerous? No. In the ground truth, it was not cancerous. Thus, the precision is 0 or 1, which is 0. There is another way to look at the previous example, which is known as the confusion matrix. We have 4 entries in this confusion matrix. The ground truth could be either yes or no, which is cancerous or not cancerous. And similarly, we could predict to be either cancerous or not cancerous. We saw previously that out of the 100 instances, 98 times when the ground truth was not cancerous, we were also able to predict it as not cancerous. Thus, the entry corresponding to predicted equal to no and ground truth equal to no is 98. For one instance, if you look at the first sample, the prediction is yes, but the ground truth was no. So the prediction is yes, the ground truth is no, which is the first row and the second column. And then if we go back, we saw that there was one sample where the ground truth was yes, but the prediction was no. So one sample where the ground truth was yes, the prediction was no, which is the first column and the second row. Now, can you think about precision and recall in terms of these quantities or in terms of the confusion matrix? But before we do that, let us make the confusion matrix more generalizable. So we now have 4 quantities. We have 4 numbers which are written as true positive, false negative, and true negative. Let's try and understand how do we remember these 4 names. Let's look at the first, true positive. The ground truth was positive and we're predicting it to be true. We're truly predicting it to be positive. Thus, it is truly predicted as positive, thus true positive. The first row and the second column is false positive. So the ground truth was not positive, but we are falsely predicting it to be positive, thus false positive. The third element is false negative. The ground truth was yes or positive, but we're falsely predicting it to be negative. So it is a false negative. And the last entry is a true negative. The ground truth was a negative and the prediction was also negative. Thus, you're truly predicting it to be negative. Now, let's come back to the definitions of recall and precision and try to write them in terms of the 4 quantities from the confusion matrix that we have just seen. So, when we talk about precision, we spoke about how correct we are when we predict it to be the positive class. Let's say yes in this case. Out of the total number of times we predicted it to yes, how accurate we were. So the first row corresponds to the total number of times we're predicting it to yes. This becomes a denominator, which is true positive plus false positive. And the proportion where we correct is the true positive, where we were predicting it to be positive or yes when it is actually yes. Thus, the numerator becomes true positive. Thus, the precision is given by true positive over true positive plus false positive. Similarly, let's think about recall. For recall, we said that out of the instances which were true in the ground truth, how many are we able to recall? So, thus, the instances which were true in the ground truth becomes a denominator, which is the first column of this matrix, which corresponds to true positive plus false negative. And the fraction which is identified correctly is the true positive, or what we are able to recall is the true positive. Thus, the recall becomes true positive over true positive plus false negative. We have another metric called the F-score, which combines the precision and recall in the following way. So the formula is given by twice precision times recall. divided by precision plus recall. It's sometimes useful to give a single number instead of giving a precision and a recall. There is another interesting metric called Matthews correlation coefficient. The formula looks fairly complicated at this point of time if you see, but there is one particular reason why this coefficient is very useful. And to see that specific reason, let's try to work out a simple example now. For the data that you've given below, where the ground truth positive and predicted positive is the largest number, 90, and the other three entries are also filled in the matrix, confusion matrix. Can you calculate the precision, recall, F-score, and Matthews coefficient? Okay, let's talk about precision for now. So precision is out of the times you're predicting it to be positive, how correct you are. For that, we look at the row corresponding to predictive positive. That becomes a denominator. Thus, the total entries are 90 plus 4, which is 94. And how many of them are we correctly identifying? That is 90. Thus, precision becomes 90 over 94. Similarly, if we look for recall, out of the entries which were positive in the ground truth, that becomes the first column. That is 90 plus 1, which is 91 entries. How many are we able to recall correctly? That is 90. Thus, recall becomes 90 over 91. And we can calculate the F-score by twice precision times recall divided by precision plus recall. Now, all of these numbers are giving an indication that we have done a very good job at identification or at prediction. But does there seem to be a problem? Yes, so the problem is that this was a very, very easy problem for classification because most of the instances were positive in the ground truth. So if you predicted everything to be positive, you will have a fairly high precision and recall and accuracy and F-score. But the Matthews coefficient comes out to be fairly low. What this is telling us is that you're not doing a substantially good job identifying or at predicting in such a case because the problem itself was fairly simple. So this is where we need to take all the metrics and all the results with a salt of grain because it is important to look at how easy or difficult it was when you could have predicted the most occurring class.
I ground truth as a vector of real numbers, and the prediction will also be a vector of real number, right? The first metric which we look at is called the mean squared error. The way to remember this is it's composed of three terms, mean squared and error, and they're computed in the reverse direction. You first compute the error, which is yi hat minus yi, right? Predicted minus ground truth for the ith sample. You have computed the error and I've also shown the corresponding color. Can you see the different colors now? So yi minus y hat minus yi tells you the error term. Then you have a squared term. So yi minus yi hat minus yi. For each sample you square the error, right? And then you finally take the mean over it, which is the mean over the n samples, right? Mean squared error. First the error, square it, take the mean. And a term which is generally then used in literature is called root mean squared error, which is the root of the mean squared error, right? There is another very similar metric called the mean absolute error. Again, it starts from the inside. You first calculate the error, yi hat minus yi, take the absolute values of it, then take the mean, right? We could have also come up with a metric called the mean error, which is first compute the error and take a mean of it. Why is that a bad idea? Use it as a metric. They would cancel each other out, right? So you could have a prediction. Imagine the ground truth falls 0, 0, 0, 0. Or you have 4 examples all 0. And you have predicted as plus 10, minus 10, plus 10, minus 10. What is the mean error in this case? Mean error is 0. What is the mean absolute error? 40 by 4. 10. And RMSE would become, of course, again calculated. So this is why it is also important to know what are the metrics you're trying to optimize on. Can anyone tell me why you might want to use mean squared error or mean absolute error at times? Sorry? Differentials. So maybe something more trivial. Sorry? Minimization or error. Okay, something even trivial than that.
That gives us breadth of I'm assuming gives us breadth of how we these things.
Okay, so can you tell me how does the RMSE, so if yi hat is very far away from yi, which is going to produce more error? Squared. So can you say that squared errors tend to penalize bad predictions much more than the regular errors? Okay, so now let's quickly get into the first algorithm for today. We're going to talk about decision trees. We are again now solving a classification problem using our first algorithm called decision trees. So we have some training data where we have the different days from D1 to D14. Should the day be included as an attribute or not? That is in your assignment, so no one will tell the answer now. We have the outlook, whether it's sunny, overcast, etc., the temperature, hot, etc., or the humidity and the wind, and whether or not you play tennis, right? So now you're trying to predict whether I should or learn a function between play tennis and the attributes of concern, right? These are, as we discussed, input features, covariates, attributes, and the output variable. And this is classification because the output variable of concern is discrete. In this case, it's only yeses or no's, right? And we could have also used decision trees for a regression case where we're trying to predict the house price given the square footage and age of the home. Right? Let's get back to the example which we were discussing. I'm not going to talk about this for now. So one of the reasons why algorithm called decision tree is studied, if we remember last time, we were discussing things like Uber and Tesla crashes. Imagine if we have very, very complicated machine learning algorithms, let's say some neural network like algorithms. There is often a case of very hard to do interpretability for these models. It's non-trivial to understand what the model learned, but decision trees being one of the very simple models are very well suited for such cases where you want the model to be interpreted. Now, imagine if you go to a doctor, right? You want to build an application, you want to build a machine learning, let's say, cancer screening application for a doctor. Will the doctor trust that I have applied sigmoid and ReLU and some saliency maps and I have done some attention and 20 other technical terms in neural networks? Or will they say that I've come up with a set of rules? If the patient has decaying cell function and the patient has some swelling, etc., then the patient is likely to have cancer. Which of them do you think the doctor will appreciate more? Probably the second one, right? Because that is more interpretable. This is also how many of us think, right? If we go back to this example, and if you think in your life, if you were to play tennis, what are the set of parameters that you take? One parameter which is not mentioned is, of course, the availability of someone to play with you. You cannot play tennis alone. But then, of course, you not want to play when it is very hot. You not want to play when it is very humid. Looking at this training data for a specific example, can you tell me some of the times you'll definitely play or not play tennis? As in, if it is overcast, I will always play. Can you tell me something like that? Okay, in fact, when it is overcast, you see, you're always playing, right? Just look at these specific roles. So can we come up with these simple kind of rules? If it is overcast, I will definitely play. If it is not overcast and it is sunny, and let's say that the temperature is mild, then I will also play, right? So this is how we are trying to build a tree-like structure, which is the output of the decision tree. So this is what we hope to learn from a machine learning algorithm called decision tree. Now this is a tree, You can see you have some root node and you have some branches and finally you have some leaves. Leaves are also telling you what is the prediction. So as we saw previously, if it is overcast, you always play tennis. If the outlook is overcast, you play tennis. But if the outlook is sunny and the humidity is normal, I can still play. It's only when the humidity is high and the outlook is sunny, I will not want to play. Right? Similarly, if the outlook is rainy, but the wind is weak, I can still play. But if the wind is strong, maybe I'll not be able to play for this specific example. Right? So this is what we hope to learn using our algorithm. We have data, we'll have some performance measures, what the accuracy which we have studied thus far, and we have experience coming from this data. So interestingly, what is an optimum decision tree that we can learn? So what is the optimum tree that we can learn? We have learned one such tree. Could you have learned many such trees? Could you have learned a tree where one of the attributes appears above, one of the attributes appears below? So there is a very old paper. Does everyone recognize this name? Ronald N. Rivest. Where have you studied? CLRS, which is your algorithms book, is by the same author, and this was published in 1976. Where they mentioned that constructing optimal binding decision trees is NP complete, which means that we can have so many different trees, it's not trivial to tell which is the best decision tree that we can learn. In such cases, what do you typically do? When it consider
all the possibilities and then make a decision.
Okay, so one answer is that consider all possible trees, but that operation is NP complete. So it's, for now, for the purpose of simplicity, let's say that cannot be done, or it cannot be done trivially, right? So we need some other solution to tell which is a good tree, right? So that is the objective, to end up creating a good tree, and which is good in the sense it's able to classify or it's able to predict accurately, right? But we cannot enumerate all possible trees. So we end up using something known as the greedy algorithm. So greedy means literally greedy. And the intuition is that at each level of the tree, we choose an attribute that gives us the biggest estimated performance gain. Right? We were looking at some performance metrics. We want something which is giving us the best performance gain, but we're only able to estimate it. We're not getting the entire accurate performance gain. We cannot get that. But greedy algorithms can be really bad. Imagine that this is you. You want to now, you're very impatient. You want to reach home early, you're very hungry. You see that there is no car over there. Right? You try and overtake, you try and take a left. And then because you've only seen this empty spot, you're not able to see these huge trucks. You take a left over here, and then you're perpetually caught behind these very slow moving trucks, which are moving at 30 kph. It would have been better if you just stayed at this spot, right, in the long run. So what we have done here is to take a very greedy decision, right? We have not considered the global picture, or we have not seen very much into the future. We have just seen what is the best I can do right now, which is just take a left, and then I'll be caught behind slow moving cars. So this is just to show that greedy is not optimal. Now we come up with the first algorithm. This particular algorithm is called ID3. There are some other variations of decision tree algorithms. We feed in three specific arguments. The first is examples, target attribute, and attributes. Can anyone tell me what do you think the target attribute is? Sorry? Output. So the target attribute is what the response variable or the output variable. Will I play tennis or not? Right? What do you think are the attributes? The features here, which were outlook, wind, humidity, etc. Those specific features. What are the examples? Examples are the set of examples are basically the matrix that we have, right? Which contains the target attributes and the attributes. Right? We'll start this algorithm by creating a root node. So in the previous case, the root node, the first was outlook. We'll first of all just instantiate this with an empty root node. Just say that if all the examples are positive or negative, or yes and no, then return root with a label plus or negative. Does this make sense to you? Do you understand what this means? So if all of the examples were yes or no, do we need a decision tree, or can we directly always predict it to be a yes or no? We can always predict it to be yes, right? There is no decision involved. There is no specific attribute which is telling you anything. You're always filling it. If all the examples, if the attributes is empty, then return root with the most common value of target attribute in examples. We'll come to this later. But for now, let's look at a recursive procedure. So this is a very nice intuitive algorithm which can work recursively. You first pick up an attribute A which best classifies the example. Now, if you go back to this tree, we picked the first attributes as outlook. So the intuition was that outlook will help us get the best estimated performance gain, or it is the best attribute for classifying the examples, right? How does the notion of best come in? We look at it in a minute. Now the outlook A was chosen as the attribute outlook was chosen as A. What are the values that the attribute outlook could have taken? Sunny, overcast, or rain, right? Now for each of these attributes, can you call the same function recursively? And you're done. That is it. That is the simple decision tree algorithm. At each level, you keep on taking the same decision. So we set the root to be A, and for each value of A, which was sunny, overcast, and rainy, you then add a new tree branch, and you also reduce the number of examples for now, right? You restrict the set of examples where the attribute A was the particular value 3. And if examples is empty, you add the leaf with the label of most common value of target. Otherwise, you call the same procedure after having removed the set of attributes on the remaining subset of the tree. So if this is looking complicated, just hold on for a minute. We'll get into the details of it. But before that, we had talked about giving the best estimated performance gain, right? How do we quantify that? So we come up with a metric, or we come up with a statistical measure known as entropy. What do you think entropy means in general? You would have studied some thermodynamics. Some randomness or some impurity in the sample. If you see a set like this, can you tell me what is the entropy of this? Randomness or disorder or the amount of inclarity that you have. Do you know the formula? Have you studied the formula of entropy? So the definition of entropy is given, you have 5 no's and 9 yeses, right? Imagine if all of these 14 were yes, right? Do you have any disorder in the system? No. Do you have anything which is uncertain? No. So then in such cases, we'll say the entropy is 0, right? If the cases were 7 yeses and 7 no's, what would you think is the entropy? So it will be very high, right? Because you're very unsure about whether it should be a yes or a no. So the formula is given in terms of minus p log p, summation minus p log p for the different classes. We had probability of no as 5 by 14. You had 14 examples, 5 of which were no, and 9 of them were yes, and log base 2 probability of no. So if you do this calculation, it comes out to be 0.94, which is a fairly high number. We also get a curve like this. So if probability of yes was 0, the entropy is 0, right? So this means that there is no disorder if all the examples are negative. And if you look at the other extreme, if positive, the probability of plus or yes is 1, there is again no entropy because there is no uncertainty in the system. The maximum uncertainty or impurity happens when the probability of plus is the same as probability of negative. Right? So we will start off with calculating an entropy of a set, and we now wanted to choose an attribute A, which is able to give us the biggest performance gain. So can you think of in terms of starting with entropy as a starting point? What manipulation or what other statistical measure do we need to tell which is the best attribute? Least entropy. Okay, but how do you calculate the entropy of an attribute? So again, so think of it in terms of you have to choose an attribute. So before you started off with the decision tree learning, you had a set of examples. You can calculate the entropy of that sample. Now you want to choose an attribute which will lower the entropy, right? So basically, if we go at this point, so we said that there was a lot of uncertainty in whether I'll play tennis or not, right? Which means that there is a lot of entropy. But if I choose outlook as overcast, I know that I will definitely play tennis, right? So there is no element of entropy involved there for those specific examples, right? So we now see that we're trying to choose an attribute, subject to choosing which the entropy becomes lower, right? There is lesser disorder in the system. So that concept is known as information gain. I'll just show the formula and then we'll play. So information gain is known as, the formula is given in terms of reduction in entropy by partitioning a set of examples S on an attribute A. So an attribute A could have taken different values. For example, the output could have been sunny, rainy or overcast. We then write the gain on a set of examples S subject to an attribute A as defined by the entropy which is of the initial system of all the examples minus the weighted entropy weighted by the number of samples you have for a particular value multiplied by the entropy of the subsets that we are getting. Right? I'll not go into the details for now. Let's assume that at this point of time we had 14 examples. We choose an outlook as the first node. The entropy of this set is 0. Right? The weighted entropy of this set is also 0. This set will have some weighted entropy, this will have some weighted entropy. Right? So let's stop at this point with the intuitive understanding that we're trying to choose an attribute which reduces the entropy. Let's meet at 11 a.m. on Saturday.